Okay, let's continue the topic. So before going to the problem of the book, as I promised for the moment equation, so I'm gonna solve another problem that is very important that you know, which is moving inverted pendulum. Okay, so this is that what you have. So this is this, and suppose that you have a pendulum here, and the angle is coming down here, theta, and the point O, but this moves with x of t. The base moves with the x of t. Okay, recording, right? Fully, yeah. Okay, guys. So can you let me know that? Can you let me know that what is the model of this? Simplified model of this. First of all, any idea, guys? Can you hear me? Anybody?
Yeah.
Okay. So this is simplified model of what you think? Give me just an answer. Okay, this is simplified model of your torso when you move. Your torso, upper body. This is your hip joint and this is the torso, that's right. Or like as Michael Jackson that he was dancing. Side is coming down. Okay, so the moving of the pendulum can be modeled as your torso over your moving hip joint. Okay, so what I'm gonna do, I'm gonna derive the equation of the motion of your torso, simplified version of the torso, and that's it. So what I'm gonna do, I'm gonna say sum of the torques around point O is moment equation. Mass moment of inertia around point O, theta double dot. Can I use that? Yes? Anybody? Can I use this?
No.
Why? I want that you say it. Why? Yes, because this point is moving, so only you can apply around here. MC. So what you're gonna do, you're gonna say sum of the forces in x direction is m x double dot of the mass center. Sum of the forces in y direction is m y double dot. Remember, in the previous case, you had your leg on the hip joints that was moving. This was moving, right? Now you have a torso. Why I'm teaching that? Because at the end of the day, I'm going to make a conclusion about the dynamics of your torso and the leg. Or this can be regarded as a one single degree of freedom robot arm on a rover on the Mars. Okay, so we don't have this. As I talked to previously, we have to calculate this. So I'm going to say position vector of the mass center of your torso, that I assume that is lumped at your head with respect to the point O. Okay, now you tell me, please, for God's sake, what's the first step in dynamics? I taught you a million times. What's the first step? What's the first step in dynamics? What's the first step in dynamics? Good. You look like a robot. Your voice was like a robotic system. So XY. That's right. Now what you're gonna do, you're gonna develop based on this. So you have I and J. Okay. So what's the I component of the mass center with respect to the point O? Obviously, gonna be this. Here is L sine theta, here is L cosine theta. Yes or no? So what is I component of mass center? Come on, look at it. That's it? Yes, plus x. Because O is moving, that's right? O itself is moving, point O, with x of t. And now I gonna be plus, because this above the datum is L cosine theta. So the velocity of the mass center with respect to point O, vector obviously, gonna be x dot plus L theta dot cosine theta in I direction minus L theta dot, because time derivative of cosine is sine, in sine theta in J. And the acceleration of mass center with respect to point O is x double dot plus L theta double dot cosine theta minus theta dot square sine theta in I, obviously, minus L theta double dot sine theta plus theta dot square cosine theta in J. Here we go. Obviously, as you know, I taught you a million times, this is your x double dot or ax, and this is your y double dot ay. Clear, everyone? Yes? Yes, guys? So now you have this and this, but now you have to find the forces in x and y direction. Obviously, if you plot the free body diagram, this is a system, you have, let me delete this and write it for me here. Also here. So you have mg here, and you have a reaction force, say Fy and Fx, reaction force from the base that is moving. But what are the forces in x direction? Relation number 1 and relation number 2. What are the forces in x direction? Come on. Anybody? Now you have to know it. This is very trivial now. What is the forces in x direction? Look at the graph. Exactly. Negative fx equals to mx double dot. What are the forces in y direction, lady? No, minus mg, because you have also mg, that's right? And m y double dot. And we have these from here. Yeah, go ahead. Like as the hip joint, when you move, your torso can make angles, right? See what I mean? Yeah, exactly. See, look at here. Suppose this is your body, huh? And this is your hip joint, that's right. When you walk, this can be your upper body. So it's moving, your hip joint is moving, that's right, like as x of t, as a function of time. Clear? Okay. Or ring? Who says that? The whole base, point O and these lines, all of them, they are moving. Okay? Okay? So what do you mean by which part is moving? Look at here. This is your base. Your base moves. Clear, lady? Okay? And whatever is connected to the base moves. Like as the cart, when you go for the shopping, this is the cart that you carry, that's right? Huh? You see that there is some can be there's a thing here, that's right? That you put some items here. So when this cart moves, this angle can change. See what I'm saying? Okay, okay. So now can I go to the next page? Okay. Yeah, go ahead. Uh, it's a good question. It's a great question, actually. It doesn't matter that how you assign the reaction forces, because at the end of the day, okay, then the sign of that shows that you assigned correctly or mistakenly. See what I'm saying? First of all, this is what is my judgment. Second, when it comes down, okay, let me show it here. What happened is, okay. When it comes down, okay, this edge gonna pushes it down, say. See what I'm saying? This is my judgment. But it doesn't matter that you assign like this or assign like that. If your Fy becomes negative, as I taught you previously, it shows that the original direction is this. If it becomes positive, means this is correct. See what I'm saying? Yes? Yes. Yes. Okay? That's a good question. So, yeah, please go ahead. Yes. No, no, because it's much simpler and physical based judgment tool that you can assign the sign of a torque or moment. See, look at here. What's your name? Chris. So this comes down. Oh my God. This comes down. That's right. This is what we want. Okay? Okay? And now mg as a force that has a torque around point O, helping the motion or resisting the motion. Now I'm asking the mg is helping the increase of the angle of theta or resisting. Okay, so its moment sign gonna be positive. Helping means positive, resisting means negative. Simple like that. See what I'm saying? So this is valid for any moment that not in dynamics, when you go to vibration ME520 that I'm teaching, to robotics, simple robots, not complicated robots, okay? Or driving any dynamic equation of the systems, you can use it for the moments. Obviously, you can make convention of the clockwise, counterclockwise, but these are not a smart way. See what I'm saying? The most rigorous things that you can do is say m moment is equal to r cross product of the f. Stick with this calculated sign respect to the coordinate system that you assigned already. See what I'm saying? But I'm just shortcutting this. I look at the problem and say, oh, its sign is positive. You don't need to calculate that. See what I'm saying? Hmm? So, okay. Can I go to the next page? Okay, so it was minus fx was m acceleration x direction. So this is x double dot plus L theta double dot cosine theta minus theta dot square sine theta okay, that's it. Fy minus mg, second line here, my double dot gonna be minus m L theta double dot sine theta plus theta dot square cosine theta, if I'm not wrong. Yep, this minus comes from here, this minus. Okay, clear everybody? So the question is that I want to derive the equation of the motion like as the moving pendulum. Oh my god. Okay, like as the moving pendulum. This is that what I want to calculate. I mean equation of the motion, differential equation that we derived in the previous class. So now you can use the moment equation, this, but around point mass center. Now you can say sum of the moments around the mass center, not around the point O, because your friend said that the point O is moving. This is not valid. I MC theta double dot. Now judging your skill, because I taught you a million times from chapter 2, what's the mass moment of inertia of particle around its own mass center? What's the mass moment of 0? Ahmad, that's you? Yeah, good. So it's 0. Okay? So now forces around the mass center. Which forces we have? Let me delete all of these because we won't use them. What's wrong with this? What? No. I'm trying to do that. Yeah. Oh my god, that's a huge one. Oh, let me do this. Oh, what's wrong? Oh, there is a malfunction in the. Oh, okay, hold on, guys. I have to stop it here and then merge them because there is a malfunction in the PDF.